Hello, and thank you for joining me for a video lesson on an amazing math topic. I think it's pretty amazing. Simulating motion with parametric equations, part of a TrigApps unit. And what you're looking at right now is a girl who is holding a bat, and she is ready to hit a baseball in the big game. So we are going to simulate the motion of a baseball that's being hit by this person at about a height of 3 feet. Now you might think, well, wait a second. Was this like Little League or what's going on? But when you think about it, if a baseball player is hitting a ball and they, I don't know, let's say they're 5'10", a pretty average height, then they're actually swinging down with the bat and hitting it at about 3 feet high. Maybe it's 2 feet, maybe it's 3.5 feet or something like that. But I hope you like my drawing. We're going to come back to that in just a moment and start out with something a little bit different. And that's this right here. I'm going to start out with this example on how to find a parametrization of the line through these 2 points. And so what that really means is come up with 2 parametric equations that model moving from one point to another point. Now, one thing that you probably know or remember from geometry is that if we have 2 points, you could sketch a line segment in between the 2 points. You could ultimately extend the line segment forever until infinity. Now, what we're going to do here is just actually sketch the line segment and come up with an equation for that. So the first thing that we should do is just get these 2 points here, A and B, sketched on the coordinate plane. So I'm going to take that point 2, 3, and here's 2, go up 3 units, and I have my point A. And that, just like in a previous video, that is where we're going to start. That is the beginning of the line segment. The first point that's usually given. And then the second point is -3, 1, 2, 3, 4, 5, 6. Way up here. And that is B. And that's where we're going to end. So then I'll just sketch that line segment, which I'm going to include an arrow, which kind of looks like a vector. And in a way it is. We're creating a path of a vector. But really it's just a line segment that goes in that direction. So the way that we'll come up with these equations is just start with the equation of a line, which basically is this. X equals x1 plus a times t. Now what that means is that our starting point is x sub 1, which is like our y-intercept, and then time is our independent variable, and it has a slope of a basically. So a is helping us identify how much t is changing based on, or how much x is changing based on t. All right, so once we get into it, you'll see how it's actually fairly simple. And we'll do the same with y equals y sub 1 plus b sub t. And that's just a different slope or a different rate of change for the actual y and t. Alright, so now what we'll do is we'll take that x1 and y1, which is basically the point A, and plug that in. And at the same time, we're going to put the ending point as well. So x, the ending point for x is -3. And the starting point for x is +2. So I'll punch that in. And then what we'll do is we'll say that time is just 1 second. It takes 1 second to get from A to B. So that means we'll solve for A here. So A, subtract 2 on both sides, is -5. Now we could see that on the graph too. If we just start at A, we could go 1, 2, 3, 4, 5 units. So x changed 5 units in 1 second. Then we'll rewrite the equation so that the equation looks like this. X equals 2 minus 5t. All right, so what that communicates is that we started at an x value of 2, and it moved -5 units in 1 second if we plug in t as 1. Okay, we'll do the same thing for y. Y ends at 6. It starts at 3. So it ends at 6, starts at 3. And B is what we don't know. 1 second is what we'll use. Now, we could use 2 seconds or 5 seconds or 100 seconds or a few hours or days or whatever, but the more we use different values, we'll come up with all these different equations. So in order to be on the same page with each other, let's just always assume a time value of 1. So y is equal to -3 plus 9t. Now, if we were to actually plug these into the calculator, these two equations would give us the equation of a line, a graph of a line. So we're going to say that this is only good from time is going from 0 to +1. So it takes us 1 second. Now if you punch that in the calculator, put your t min as 0 and your t max is 1, it will only sketch a segment. And that actually is pretty powerful when it comes to applications. So that's that. That's a very small idea in the big realm of parametric equations. But the last video that we studied, we basically did the other thing. We took the two equations and we went the other way and eliminated the parameter. Now the next thing, we're going to transition into simulating motion on the graphing calculator and how to actually do that by hand. And there are two different types of ways to do that. One is using horizontal motion, where it's basically movement along the line. And the way that we'll do that is, well, the way that we'll use our calculators is we will set x equal to the function, so x equals f of t, and this is a little bit general here on purpose. And what we could do for the y component of the parametric equations is set y equal to t or -t. So it's pretty hard to do this in a video. It's best to just chat one-on-one and use the calculator together. But basically there's usually something in a text that will show you the reason for both of these. But just real quickly, the idea is that if we're modeling horizontal motion, it's pretty hard to see that on a calculator because there's a particle that's just moving left or right, some sort of object, and it just creates a horizontal line. So it's hard to see the actual motion, and especially if it's something that's moving left and right. But if we allow our calculator to be programmed in such a way where y is changing based on time, you'll end up getting a curve that looks something like this. And then you'll be able to tell when the object changes directions, which is kind of at the end of here. So this horizontal motion is representing position of a particle. Now what's a little bit more important for us right now is how we could actually model vertical motion, not straight up and down, but something other than 90 degrees. And so I'm going to give you two equations here that we're going to work with. And the first one is the x component. And basically, the x component is equal to the velocity, the original velocity of whatever we're talking about, times cosine theta times t, t for time. Cosine theta gives us the actual value, how much t is changing based on the angle. And then the y component is a little bit more complicated. We have gravity that's affecting the y height, y value. And so -16t squared, so this is for feet, by the way. This is not meters. So -16t squared, this is gravity, plus v sub 0, the initial velocity, times sine 45. Not 45, what am I thinking? I'm already thinking about the example. Sine of theta. Theta is in degrees. Okay, so sine theta t plus y sub 0, and that's the initial height. Initial height. And I guess if we were to say something about v sub 0 times sine theta, this is like the projection. Nothing very complicated here, just like how this object is projected. So in essence, the actual equations are fairly simple because they're based on trigonometric stuff you studied already. But when we actually try to graph them and see the motion on the calculator, we have to be really aware of the window settings that we put in there. So I'm going to help you understand a little bit how to do that with this next example. And so here it is. The example is that Emily hits a baseball at 3 feet above the ground with an initial velocity of 150 feet per second at an angle of 18 degrees with the ground. And we're going to find out if the ball will clear a 20-foot wall that's 400 feet away. All right, so now just bring your attention back to those equations. that we just basically need to create these equations based on the problem situation. So I think this situation is actually really interesting. Somebody's hitting a ball and we're going to see if it's a home run. So let's see if we could hit this example out of the park here. So what I'd like you to do, if you have this printed in front of you, is I want you to underline 3 feet, 150 feet per second, and 18 degrees. We're going to take that information and create the equations from that. So here goes. X equals, and we'll worry about the other stuff later, 150 feet per second times cosine of 18t. And I use parentheses so we know that t is not being evaluated by cosine. So that's the x component. Now you might think, ooh, component, is that like a vector? In a way it is. It's the x component for a particle that's moving, or an object. Alright, now y equals negative 16t squared. If we're in meters, it'd be negative 9.8t squared. And so then we're going to add 150 feet per second times sine of 18 times t plus 3. So those are just simply the equations that we're going to punch in the calculator. So if you have a TI-84 handy, we're about to use it. And I want to tell you some settings here. So the mode that we need to be in is parametric mode and degrees, because we're working with degrees, 18 degrees. So we'll enter this into the y equals. So after you change the mode, go to y equals and enter this in, and then you can pause me. I'll share 3 sets of settings with you, t, x, and y, so you can actually see this. The first one is t's, min is 0, 3, and max is 3, and then the t-step, somewhere around 0.1. It doesn't have to be exactly 0.1, but if it says 0.13 in your calculator, you're good. Okay, that should all look good when you graph that. So if there's an issue, just check back. The most common mistake is students don't put the t squared, and then they'll put cosine for both, or sine for both, or something like that. So we'll pass Emily here and take a look at how to solve this actual equation. Alright, so now that you see the actual visual, I'm going to show you what some of those values mean here. So we're wrapping this up here, and I want to basically show you how you could do this by hand. So because the wall is 400 feet away, that means x is 400 after a certain amount of time. And so that's what we're trying to figure out. How much time did it actually take? So we're going to solve for t. That means we'll divide by 15 cosine 18. So you get 400 divided by 15 cosine 18. So if I go to my main screen, just press second mode, I'll get that time is equal to 2.8 just by entering that in. And probably want to do parentheses just to be sure. So that means 2.8 seconds it takes the ball to reach the wall. But we don't know how high the ball is, so we don't know if it's going to be a home run or not. So we're going to take that 2.8 seconds and plug it into this y equation. So we get negative 16, and I don't actually have to write this. And you wouldn't type it in on your calculator anyways. You would just enter second answer. Furthermore, you could actually take a shortcut on your calculator, and I'll show you how to do that. So on the main screen, you could just type this in, and you could type y equals, and then type it all by hand. But it's actually a lot quicker to go to your graph again. So press graph, you'll see it sketch. It might not actually take time to sketch again. And then press second trace value, and then you could type that 2.8 inside there. Now for the most part, it's okay that we leave some decimal places off. So just go ahead and type in 2.8 and you should get 7.2-ish. And that's 7.2 feet because you plugged it into the y component, which is basically a height. So if we were to go back to the question, notice 7.2 feet. And if you press second trace and hit value, you should see that on the actual graph. And it should be pretty close to the end at 400 feet or so. And if you look at what the question is asking, will the ball clear a 20-foot wall that's 400 feet away? Well, no. 7.2 feet is not even, what is it, just a third? It's not close, no. If it was 20, I might say, well, maybe it could bounce. But 7.2 feet, too short, so no home run. Sorry, Emily. That was a nice hit, but it just wasn't quite a home run. Maybe, though, it hits the wall and is a double or a triple, depending on that. Okay, so I hope you have enough tools to actually solve a question like this. You could go back to the video and see some of the steps, but basically, if you were to take that value of 400 feet and plug it into the equation 2, you could also just see it on the calculator. But now you have the algebraic and the graphical way to do that. All right, thanks a bunch.